Hello friends, welcome to Saurav Sir classes. The topic of this video is analysis of variances, or what we shortly call Anova. Anova is a procedure that can be used to test the equality of three or more means in one test. Suppose, for example, there are some professors in a university that have decided to experiment with three different teaching methods, and they want to find out if these methods produce different results. Let μ1, μ2 and μ3 be the mean scores of all the students who will be trained by these newly devised methods. To test whether these methods produce different results, we test the hypothesis H0, that is, μ1 is equals to μ2 is equals to μ3. That is, all the population means are equal. This hypothesis is called Null Hypothesis, and we will test this hypothesis against the alternative hypothesis that not all the population means are equal. That is, there exists at least one pair of means which are significantly different from each other. Now, the question may arise, why this procedure is called Anova, or analysis of variances. The reason is that this process involves a systematic way of partitioning the total variability into the different components associated with nature of classification of data. For example, in our professor example, the variability between the scores of students can be classified into two parts. The first part is a variability due to different teaching methods, and the second is a variability between the scores of two students taught under a particular method. Now, one-way Anova. One-way Anova is a type of Anova in which we analyze only one factor, and the data are classified into different groups based on the different values of this factor. These values can also be called the levels of the factor. Let us suppose there are k levels of the factor. Then the null hypothesis of this one-way Anova can be given as H0 is μ1 is equals to μ2 is equals to so on to Msqe. That is, the population of all the samples have same mean. This null hypothesis is tested against the alternative hypothesis, that is, there exists at least one pair of means which are significantly different from each other, where I and j belongs to 1, 2 and so on till k, and I is not equals to j. One-way Anova has certain assumptions. The first assumption is assumption of independence. That is, the samples drawn from the population are random and independent. The second assumption is assumption of normality, that the distribution of population from which the sample is selected are normal. And the third is assumption of homogeneity, that the variances of different population are equal. Let Yij be the random variable which represents the jth observation under ith factor, where I would run from 1 to k and j will run from 1 to ni. Here ni is the sample size corresponding to ith factor. The model used to describe the observation Yij can be written as Yij is equals to mu I plus Eij, where mu I is the mean associated with ith factor and Eij is the random error component. This mu I can be further written as mu plus Ti, where mu is the mean of all the population or the overall mean and Ti is the parameter associated with the ith factor. So Yij can be written as mu plus Ti plus Eij. This is also known as effect model, where I runs from 1 to k and j runs from 1 to ni. These effects can be fixed. This can be a fixed effect model or random effect model depending upon whether the levels are pre-considered or selected from a random population of levels. If it is a fixed effects one-way Anova model, we have summation of Ti, where I runs from 1 to k is equals to 0, or summation I is equals to 1 to k ni Ti is equals to 0. Estimation of parameters and sum of squares. The least square estimation of mu and Ti can be obtained by minimizing this equation double summation, where I equals to 1 to k and j is equals to 1 to m Yij minus mu minus Ti square, which is the sum of squares of error. I is equals to 1 to k, j is equals to 1 to m summation Eij square. Here we can see that instead of writing ni, we have written m, because we have made a simple assumption that all the samples are of same size, that is ni is equals to m for all I. Now when we will minimize this with respect to mu and Ti, we will get the estimates as follow. Mu cap is equals to 1 by km summation I is equals to 1 to k summation j is equals to 1 to m Yij, which is equals to y double naught bar, and Ti cap is equals to yi naught bar minus y double naught bar, where yi naught bar is equals to 1 by m summation j is equals to 1 to m Yij. This y double naught bar is called the grand sample mean, and yi naught bar is called the mean of ith factor level. Now we can write Yij as y double naught bar plus yi naught bar minus y double naught bar plus Yij minus yi naught bar. which is equals to Yij minus Y double naught bar, which is equals to Yi naught bar minus Y double naught bar plus Yij minus Yi naught bar. Now when we will square the both sides, we will this equation where this is the total sum of squares, this term is the sum of squares due to different factor levels, and this is sum of squares due to error, or TSS is equals to SSB plus SSE.